All right, I will say things. Heavenly Father, we thank you for this day again, Lord. I thank you for the students. Just ask you to help us in this time just to glorify you what we do, Lord. In your name I pray. Amen. So we were working on an example back before the break. What did we come to? What was the matrix we found? In the... It was pairs. It was over R cross R. 1, 1. Up here. And what? Minus 1, minus 1. And we engineered this to have, what were the eigenvalues? 2, 3, and minus 2 and minus 3. Okay. In pairs? Oh, I'm sorry. Yes, the I forget, like this, right? And so there's 4. Those 4 what's that? That's all the roots. Is the spectrum bigger? I am curious, what's the spectrum of A? So that would be what? So we're looking at A comma B such that what? A, B, oh, that's still like, such that there exists V in R cross R 2 such that what? Such that AV equal to AB V, right? And so what did you say the... Did you hear that? I turned off the kids have been playing with the minion rush, so now the push alerts are going beedo, beedo. Minion rush, come back. The longer you stay away, something out here. All right. Anyway, so you're saying graphically. Are they the like vertical lines? Oh, is it like? So it's. I mean, I would think it would be x equals to minus 2, x equals to 2. If what you're telling me is right, y equals to minus 3, y equals to 3, you know, ignoring, of course, the coordinate axes, which I've just drawn because, well, just so. Hmm. Let me think about this. If we have AV, right, equals to 2, 3, V, I mean, such a V exists, right? And if I multiply this by, say, 1, 0, what happens? But what happens when you multiply this, you get what? We get, of course, we get 2, 0, V, right? Which we can rewrite as so that shows that the existence of the eigenvector for 2, 3 implies that this thing is an eigenvector with eigenvalue 2, so lambda basically 2, 0, that's part of the spectrum. And then you can scalar multiply that by any constant, I think, to get that K0 is part of the spectrum. Wait a minute. Is that always going to be 2, 0? I said something after that I'm not actually sure about. 2, 2? I'm not. Like, what happens if I multiply this by? Just try multiplying it by, K0. What does that do? I mean, right? But then I can play games with the. Well, I guess I need that here though. And I need another copy of that on the other side to make up the new eigenvector. So I see I get 2, 0 in the spectrum from that. But you're saying there's a lot more.
Well, I say a part of those four, like
So it's in these 4 lines, but it's not all of these 4 lines, is your belief. So this is what we found for the roots, these 4 points, right? If we're thinking of it graphically. And I just showed by multiplying by the E1 that we generate the spectrum, we generate 2, 0, which would be what? Wait a minute, 2, 0, where's that? Oh, that's here, right? And I guess it's somewhat clear that if we took, then yeah, if we put a -2, we'd negative. I mean, so we get -2, 0 from the other root, right? Yeah, if we multiply by like E2, that would pick up these points. But Kang is saying there's much more than just those. Based on what? You just straight up calculated the. I mean, it doesn't much matter, right? The theorem that we talked about last time, it doesn't use the spectrum, it uses the roots to do things. I'm just interested in the spectrum for no reason other than just my own raw curiosity. I don't think it really helps us do anything in particular. But again, I think it does illustrate what I was speculating, which is that we have kind of two different cases. We have eigenvectors which are good, that can be extended to a free module basis, an A module basis, and we have those which cannot. These cannot, because this is a linearly dependent vector. The singleton containing just this vector, when you multiply it by E2 times this is 0. So, so that shows that there's a non-trivial linear combination of that vector, which gives you 0, which means it's linearly dependent. So that can't be part of a basis. So yeah, 0, 3, 2, 0, minus 2, 0, 0, minus 3, these are part of the spectrum. They do have eigenvectors, but those eigenvectors are in some sense degenerate. Yeah. In the sense that we can't extend them to. So did you guys find the basis for me? Corresponding to the roots? Like what? Did, 2, 3? The vector is what? 1, 1, 1, 1? All right. I'm going to call that V 2, 3. And that gives us vector what? Minus what? Minus 1, 3? Okay.
Oh, no, I mean minus 1 from.
Ah. Oh. What were the eigenvectors for minus 2, 3? One, 1. And what was the eigenvector for 2 minus 3? And what? Huh. So these are our eigenvectors, yeah? Four cases? You said there are 4 cases?
No, there's only 2 cases. Like the first 2 is a form of basis, and
Let's say possible bases of eigenvectors for roots of A. So what was the first case? Just the first 2. So let's say beta. I'll call it beta 1, which would be your V2, 3, and V minus 2, minus 3. Anyway, to be more specific, you got your 1, 1, 1, 1, 1. Maybe I put too many 1s in there. Sorry about that. And are you sure that that's not actually minus 2, minus 3, 6, 6?
no, I checked the multiplication too. I first thought that I was wrong, but then I forgot.
I mean, wouldn't it be lazier to multiply this by 6?
I mean,
But you've already done.
better than you should multiply it by 3 too, I guess.
Right. Oh, multiply by 3, 2. Very good. So multiplying by 3, 2 will give us minus 1, minus 1. Or how about, let's multiply by minus 3, minus 2. So at least we'll have 1, 1 up here, which is nice. And minus 3, minus 2. That's your first alleged basis. How did you prove that that's a basis for two tuples of direct product, like R 2 by 2 by 2? Sorry, R cross R, two tuples. It's obvious because they're not scalar multiples of each other.
No, I mean like just form a linear combination and then make it somehow equal to some random vector of two tuples in general case.
So you showed that these actually span.
Yeah, span first and then this is how actually.
That's an interesting approach. See, I've been, and I probably would slap these things in a matrix, calculate the determinant. If the determinant is a unit, then, you know, so, but the advantage of doing what you did would be that you would actually have formulas for change of coordinates and stuff with respect to this basis from what you did. Because if you actually solve that linear dependence, that means you have a way to restate a given two-tuple of two tuples in terms of a specific linear combination of these two vectors, which is to say you understand the coordinate map. So that's not bad. But I'll be lazy. This is a nice basis because it's got like mostly identities, you know? See, 1, 1 is 1 in the algebra R cross R. So this is, you know, just, yeah, minus 3, minus 2, minus 1, 1, which is, yeah, minus 4, minus 3. And that is an element of, well, I'm trying to start using this notation, the units of R cross R. Anyway. So we could construct the, let's see here. So we can construct the diagonalizing matrix, right? We can look at beta 1 inverse A beta 1, right? And if we sort through that calculation, what should we get? We should get 2, 3 for the first one, right? 0, 0, and minus 2, minus 3 down here, right? Of course, those are 0, zeros. I'm not sure it actually matters that we actually sort through. I mean, you guys know how to calculate the inverse of a 2 by 2 matrix. So we can do that. But I guess that might be, well, I guess it's not that interesting to do. Okay, so great. We can diagonalize the matrix A with respect to the beta 1 basis. So I'm going to put sort of a reformulation of this. This is 1, 1, minus 3, minus 2, right? And this one we could relook at. We could instead look at this as what? This is I guess 1, 1 and 3, 1, right? Negative 3, 1, yeah. And this we could look at as 1, 1, 1, and 1 minus 2. to get rid of the fractions. Then the question is, which of these pairs, is any choice of these, is there any linear dependence between these?
And
Just taking two at a time?
oh no, exactly. There's just two pairs that can form a basis.
Okay.
The rest is
So your claim, we've already seen number one. What's number two? The last two, so beta 2. So like 1, 1, minus 3, 1, and 1, 1, 1 minus 2. Let's see here, just to check my sort of quick and dirty way. The determinant of the matrix is 1 minus 2 minus 3 comma 1, also known as 4 comma minus 3. Excuse me. This 4 comma minus 3 and this minus 4 minus 3, how do these relate to the eigenvalues? Let me give these some names. We call this lambda 1, lambda 2, lambda 3, lambda 4. I believe this should be lambda 1, lambda 2. Am I wrong? What's that? Oh, yeah. So it's not. Oh. Really? Really? Oh, I'm worried now. I thought the determinant's the product of the eigenvalues. Oh, I'm talking about the determinant of the, I'm an idiot. We're talking about the determinant of the basis matrix. That's nothing. I'm sorry, that's not, duh. If we reorder the basis, we change by a sign, stuff like that. This is no particular significance in that sense. The determinant of A, it should be the, whoa. What is the determinant of A? Looks like minus 4 minus 9. That's interesting. The basis choices that you found are the ones for which the eigenvalues product actually corresponds to the determinant of the matrix. See, the determinant of the matrix is minus 4 minus 9. If we take the product of lambda 1, lambda 2, we get minus 4 minus 9. We take the product of lambda 3, lambda 4, we get minus 4 minus 9. But if we take the product of lambda 2 with lambda 3, we get 4 minus 9. Or 1 and 3, we get 4 minus 9. Or minus 4, 9. Only those two pairs have the property that the product of the eigenvalues is the determinant of the matrix. I wonder if that's an accident. The trace. The trace should be the sum of the eigenvalues. So the trace of 1 and 2 or 3 and 4 is 0. And the trace of A is 0. Neat. So maybe that's a guide for determining how to select the free module basis from your root vectors, from the eigenvectors for the roots. perhaps this is a guide. It took us some effort to come up with this example, yeah. I'm not done with it yet, right? All right, so interesting. So, and you've checked also the other cases don't work. Like if I try, for example, 1 and 3, I put these, let me just, 1, 3, I would have 1, 1, minus 3. I'll do this one and then the other one. So you end up with the determinant of that. So you get 1, 1. So you get 4, 0, is that what it works out to? And that indeed is one of the zero divisors, right? I bet there's a theorem we can prove that if the the product of the eigenvalues, I wonder if knowing the product of the eigenvalues and the trace of the eigenvalues corresponds to what they should, namely the trace of the matrix and the determinant of the matrix, is that data sufficient to say, oh, okay, well that choice of that set of eigenvalues that I don't think that's going to be enough generally, because if you just so 2 by 2 is special. In the 2 by 2 case, knowing the trace and the trace and the determinant allows you to solve for eigenvectors, eigenvalues, because it's 2 equations and 2 unknowns. You're looking for lambda 1, lambda 2. If you know determinant and you know trace, you can figure out what lambda 1 and lambda 2 are. If we're working at a 3 by 3 matrix, it's no longer the case that the determinant and the trace is enough data to figure out what the eigenvalues are. See, because there's 3 eigenvalues and you only have 2 pieces of information, the determinant and the trace. So they offer guidelines, but they don't fix the eigenvalues. So I have a sneaking suspicion that what we're doing, this pattern we're observing when we try to say what it is for 3 by 3 matrix, we'd need to be more sophisticated. I think something could be said here, though. All right, so anyway, I'm happy that you've checked on what space is here, what's not. It's good. Now we should do what? We should go and we should look at the solutions to the differential equation and see what the difference is, right? Can we get from one kind of solution to the other? All right, so with basis 1, what would our natural solution be? Let's say R1. I guess I should say of xy, right? It should be e to the lambda 1 xy times, v2. What is it? What did I call it? Well, let me just write down the stupid vector. 1, 1, 1, 1. All right. That would be my first. And my second solution, e to the lambda, which I probably should just write down what the lambda is, right? What is my lambda? First one, 2, 3. And here we're looking at what? Minus 2, minus 3? Is that right? xy. What's my eigenvector? 1, 1. Minus 3, minus 2. So this is equal to e to the what? E to the, this multiplies to 2x, 2y, 2x come 2y. And if you work on this, I'm pretty sure we have the following identity. E to the 2x comma 3y, let's say. is e to the 2x comma e to the 3y. Is that right? Yes. I'm thinking about power series when I say yes. All right, there's that one. And this one, so those together as a pair form a fundamental solution set to the differential equation. These collectively will solve dr d, well, for lack of a better notation at the moment, xy, right, equals to AR, I believe. Because if we differentiate with respect to xy, e to the xy lambda times eigenvector, we get lambda e to the lambda xy eigenvector back again, which when you multiply by the matrix gives you back, it works out. Okay, so I derived that last time, I think, right? So both of these solve, and so the general solution would look something like, C1 R1 plus C2 R2, where C1 and C2 are, of course, pairs in the algebra, right? These are algebra constants. Now, that's the first solution. What does the solution look like for beta 2? Right? Because it seems like we get a different solution for the beta 2 basis. We get R3 of xy equal to, let me just get straight to the point. You know what's going to happen. E to the minus 2x, e to the 3y, the eigenvector, which was, what was it? It was 1, 1. Is that a minus 3, 1? I can't quite read it from here. And then R4, xy equal to, let's see here, e to the 2x, e to the minus 3y, and what we got? 1, 1. What'd you say? 1 minus 2? Okay, so those collectively form a fundamental solution set to the system. So, does that seem... Are they the same ones?
I mean, like, you have the same combination. If R is C1, R1 plus C2, R2
Let me see here. So this is actually e to the minus 2x, e to the 3y, minus 3 e to the minus 2x, e to the 3y. And of course this one is e to the 2x, e to the minus 3y, e to the 2x, minus 2 e to the minus 3y, versus these guys, which is e to the 2x, e to the 3y, e to the 3y, e to the 3... I can't do math. 2x, right? 3y. And my R4, which is e to the minus 2x, e to the minus 3y, minus 3 e to the minus 2x, minus 2 e to the minus 3y. I got to sit down. I won't see it standing up. Ugh. So what were you saying, Kang? Where's my laser? Ah. They're like swapping arguments. Oh, yowzers. But the minus, are you talking about this and that? But there's a minus here, there's a plus there. But this is literally, nope, there's a minus 2 here. I don't see any particular pattern, do you?
I think this error one is if you have R equal to C1 R1 times plus C2 R2, then you will also have C1 R equal to C1 R3 plus C2 R1.
Oh, you can start to see how they provide the same general solution when you look at the linear combination of R1 and R2 and R3 and R4. Okay. If you take linear combinations of both of those, you get the same kind of flexibility. Yeah. Same coefficients even.
But if you have C1 times R1 plus C2 times R2, then it is equal to C1 times R3 plus C2 times R4.
If you have, what did you just say? C1 what? Uh-huh. Plus? Okay.
It has to be equal to C1 times R3 plus C2.
R4? Oh, Cooper, are we looking at this right now? Hey, hey. Hey, hey. It's okay. R3. I'm sorry, I should write down. This is R1, right? Right? R1, R2. So C1, R1. C1. Oh, okay, okay. Yeah, I don't think it's that simple. Now here's something. But, you know, it's not bad to speculate. Well, okay, so here's something, a homework exercise I'm fond of in differential equations. Given any two fundamental matrices, right, for a system of differential equations, right, a given system, you can prove that there exists a constant matrix that when you multiply one of the solution matrix, you get the other. Did you know this? The reason is pretty simple. It's because we go. So if you have x is got like x1, x2, xn, and then you have another solution matrix y. The thing is that each y, right, like y1 has to be equal to c1 x1, c11 x1 plus c12 x2 C1n xn, why? Because X is a fundamental solution set, so you can build any solution, in particular Y1, from it. But you can just as well do this for the, the ith one. And when you look at that, what that gives you is well, sorry, bit off more than I can chew. So, for example, y1 is C11. How to write this? These are vectors. That's a vector. Yeah. Okay. So it is the X matrix times the C, C11, C12, C1n. And so then when you look at the ith one, so then if you just put these together, you get just by the row by row multiplication rule, I think you end up with like we have y. I'm sorry, I'm having trouble with words at the moment. And then this is what? This is the so my numbering of the constants is unfortunate. See, because what I should really say is we've got this matrix B ij, which is equal to Cji. And if I did that, then you'd see that this is nothing more than the jth column of B, right? And so forth. So my point is that we have that if we put those all together, we get the matrix Y is equal to the matrix X times B. And B is a constant matrix. And in fact, it's pretty easy to calculate what B is. Because if B is a constant matrix, well, Y of 0 is equal to X of 0 times B. This is especially useful to calculate the matrix exponential, see, because e to the ta is equal to, well, any fundamental matrix you got, right, times some constant matrix B. So to figure out what B is, plug in times 0, you get I is equal to X of 0 times B, which then tells you that e to the ta is actually just equal to X of t times X inverse of 0. That's where that formula comes from, to calculate the matrix exponential from a given solution matrix. Anyway, I'm sorry. My point was there's something interesting to think about here. There has to be a matrix, a constant matrix, which takes you from this solution matrix, right? There has to be a constant, I think, if there's any justice, what do you want to say? If I take this solution matrix, I can take, the other solution matrix, R1, R2, and I can multiply by some B, and I can find a constant matrix which takes me from one to the other. Because the arguments leading up to that, the argument over there is not based on field argumentation. It's based on linear combinations of solutions being solutions, and the solution matrix giving a general solution. Those things are still in play by my existence and uniqueness theorem. So it stands to reason there's some constant matrix B that connects these two. I don't know. I'm not you. Oh, us. Well, this one's going to be really hard to find because so yeah, I don't know. Oh, so that's actually kind of, there's a fairly clear path of what to do, because this gives us that the b is what? It's R3, R4 times, I can't do math, this one, right? Inverse. And since B is a constant matrix, you might as well do this for when x and y are both 0, right? And that's not too bad. I mean, what is... Let's call this thing x34, and let's call this x12. So, like, what's x12 and what's x34 here? Say it again. What is x12 of 0, 0? Okay, right. It's just the basis matrix. You're right. Right. Which was 1, 1, 1, 1, 1. Lots of ones. First column. And then 1, 1. And then my x34, 0, 0 is 1, 1. And, okay, so allegedly, the b to take me from one to the other is, what was it? R12, so x12 inverse times x34, right? So what is x12 inverse? Well, the determinant, we discussed this already. Right? 1 over minus 9 minus 4. Oh, yeah. So sorry. Flip the diagonals. Oh, I did? Oh, thank you. I'm still stuck on that thing I want to be true, right? So minus 4, minus 3. You know, sometimes you believe in something so much, you just make it happen, right? Let's see here, 1, 1. Whether or not it's actually true. Let's see here, 1, 1. Flippity floppity. Minus is on the off diagonal. And then that's times x34, which again is I mean, this should help us actually to find the thing that King was trying to eyeball. Right? I mean, now here's something fun. In the direct product algebra, do you know, guys, do you know what 1 over a comma b is? So many things that we yell at freshmen for doing are actually true here. Like, it is, in fact, 1 over a, 1 over b. So sometimes I'm looking at Calculus 3 students the wrong way. I should just give them credit. They're thinking in the direct product algebra of R with R. They're not really working with geometric vectors. They're abstract algebraists. So just looking at it the wrong way, you know? So yeah, anyway, so 1/4, 1/3. I'm absorbing the minus over into here. I'm just going to leave it out front. That way I can lose it. Yeah. So this times that is what? I guess I better write down 3 minus 2 plus 3 minus 1. Minus 1 minus 1 plus minus 3, 1. 3 minus 2 plus minus 1, 2. Minus 1 plus 1 minus 2. So let's see here what we got. We've got a 6 minus 3, 2, 0. Uh-oh. Sometimes, every time I see something like that, it just makes me go, Sorry. Zero divisor. I'm scared of zero divisors. Now that is, that looks like a minus 4, 0. And 0 minus 3? Oh, no, 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 no. That's no point. Oh, wait a minute. Hold on a second here. Gotta reserve judgment. Okay, so fine. What do we got? Is there something wrong with my calculation? Oh, my x1, 2 is wrong? Oh, negative 3, negative 2. Oh, no. All right. Let's see where that trickles. So first of all, here. What's that? Minus. What happens here?
Like, I guess that changes, but you still have a 0.
There's 0 here too, right?
Yeah, 0 divides 0
Well, that's better. This is, to me, this is more, it's better. I mean, I like this better. It's more symmetrical. There's not this one weird non-zero divisor component. What's that? Negative, where?
Second column, first row.
Ah, that's even better. Ah, ha, 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 ha. Okay, so now we multiply this through, we actually kind of get some nice stuff, right? So we get like, what, 0? Oh, that's pretty. Oh, this is really cool, guys. You know what this is working out to? What's the determinant of this matrix? When you calculate the determinant of this matrix, you get, oh, it's not quite what I thought it was. I thought the determinant was just 1, 1. It's not quite that. It's negative 1, 1, which is fine. That's a unit. In fact, it's its own inverse. Negative 1, 1 times negative 1, 1 is 1, 1, which is the identity in R cross R. So that's good. Now, allegedly, if we take that matrix, right? If we take that matrix and we multiply it on the right of R1, 2, we should generate R3, 4. Are we brave enough to try it? Do I have room to try it? Oh, there's 4.4. You're right. Thank you. All right. So you guys tell me what is R1, R2? And then R2 was e to the minus 2x, e to the minus 3y, minus 3, e to the minus 2x, minus 2, e to the minus 3y. And then we're supposed to multiply that thing by the b we just found, which is ever so very simple. So again, what we're looking at here is x1, 2, b. We're hoping to get x3, 4 from that. So this times that picks me up a e3y plus this piece gives me a e to the minus 2x. And then this times that gives me a e to the, did I do that wrong? Sorry guys, I'm trying to do too much in my head. Let me just recenter. Try that again. So this times that, the first component comes from this times that, which gives me e to the minus 2x. Then this times that gives me the second component, which is e to the 3y. Then this times that, again, this times that picks up my first 3e to the minus 2x. And then this times that picks me up that e to the 3y. Then here it gives me an e to the 2x, e to the minus 3y, and e to the 2x minus 2 e to the minus 3y. Ha-ha! All right. So I think we have demonstrated today that yes, there are 4 eigenvalues, and so we get 2 seemingly dissimilar fundamental solution sets, but they're not really. They're linearly dependent one on the other. We can find a matrix which changes one solution set to the other, just like that. And let's see here. What can we say? What can we say about what is the relation of, say, beta 1 and beta 2? Let's just try to get the most we can out of this. This had eigenvalue lambda 1 equal to 2, 3, lambda 2 equal to minus 2, minus 3, right? Beta 2 had lambda 3 equal to minus what? Minus 2, 3, and lambda 4 equals to, what was it? 2 minus 3. So what happens when you take the